Good morning, ladies and gentlemen. My name is Misty. I'm a member of Belarus team, and I want to present you the solution of the problem number 13, Misty. Let's start with formulation of the problem. Based on the cold glass surface, so that water vapor condensates on it. Look at the white lamp, so the Misty glass, and you will see a color flash ring appear outside the central lights with a spot. Explain the phenomenon. At this slide, you can see the demonstration of our phenomenon. It's a fuzzy spot, dark area, and color free. At the beginning, we want to prepare you the plan of our proof. First of all, it will be qualitative explanation of our phenomena. After that, we will have the experimental part and understand which parameters have influence on our phenomena. And after that, we will build a mathematical model which can predict our answers. First of all, a qualitative explanation. We have a light source and glass with drops. When our waveform put on the glass, because we have drops, we have a diffraction on it. After that, we have a lens in our camera or in our glass, and after that, we can see the image. Okay, but not only between drops are our waveforms. Our waveforms or our rays put inside the drops too, and as you know, the refractive index between the refractive index of air and water are different. That's why we have a different phase. This way, when the rays passing out the drop have a different phase, and that's why after they interact, we can observe diffraction patterns. Okay, we have small drops, and maybe we can say that in small drops, different phase are really small. That's why we can say that we want to calculate only diffraction between the drops, and we can have a big drops. In this case, we can't neglect the different phase, and that's why we must calculate it. Okay, about experimental part. It's our experimental setup, the light source, and the glass, at which we can observe our ring. And the interesting fact about our experimental setup, light source is the light amplitude, and focal distance in camera was infinity. It's important for us. And we built the intensity distribution for three different colors, use the RGB method, and our graph starts at this point, and as you can see, first of all, the blue color are higher than others. That's why we can observe a blue ring. After that, we have a small part with when our green color have a biggest intensity, and it's small green and maybe yellow ring. And after that, we have a red border. We used different wavelengths, and as you can see at this slide, the maximum for different wavelengths has a different coordinate. That's why we can observe different color in our colors in our ring. For example, we built the intensity distribution for blue color, and you can see that we have not only one peak which we observe when we have a different color on our pictures. We have a different peak too, but because in this coordinate intensity of other wavelengths are bigger, we can't observe it. Okay, about the parameters of the drop. At this slide, you can see the photos of our drop in the glass, and we can say the drop diameter are like 30 micrometers and less. Drops are positioned on the glass randomly. It's very important, and the drop has a random shape. It is important too because we can't neglect it. And at this videos, you can see when we breathe on our glass. First of all, our drops are small, but after that, their linear parameters, their radius increase. And how it influences on our image. At this video, you can see that the maximums change each other, and that's why this coordinate depend on the radius on drop. And the interesting parameters is the type of light source. It's this picture for light, and it just this picture for intense lamp, and for solid lamp. You can see that the biggest quality of color we can observe in case with light and diode. And that's why we can say that diode has the most appropriate spectrum, because its spectrum has no dominated wavelength, so we get a pattern where almost all light can be observed. And it's great for our experiments. About side of vapors, it's the inner side, which are side on the observer, the outer side, which are for the light source, and when our vapor are at both sides. And then you can see that the clearest picture we can see in this case. It's because when our wavefront put on this border, our rays are plane, our wavefront are plane, and we observe only diffraction in on this part. But when we have this case, we have a diffraction, and after that, it's increased by our drive. That's why our picture is moving. When we have a condensate on both sides, we have two different diffraction picture which put on each other. That's why our picture are really smooth. And really interesting phenomenon that we can observe this picture, but we can observe other intensity distribution for different wavelengths. That's why we can see that first of all we see a red color, but after that see blue color. We want to explain why it's possible in our mathematical model. First of all, because we have a diffraction, we can calculate it use the Huygens-Fresnel's equation, which calculates our diffraction picture and increase the difference phase. That's why we can use it like for small drops and for the big drops. But for small drops, we can use the every formulas too, because we can neglect the difference in phase which we have inside a drop. We built the intensity distribution on coordinate for small drop, use the area equation and Huygens-Fresnel formulas too. And you can see that graphs are really similar. That's why we can say that our theory really works, and we can say that small drop can be considered like this, as the plane shift is short, and this wave gives almost no addition to the result pattern. So the interference of waves from interval between drops is the only reason in this case. But about the big drops, we have, as I said, we have a different phase. That's why for big drop, we consider the ray spacing thousand drops, and the reflected index of it's because of reflected index of the water depends on frequency. And we built the theoretical distribution using Huygens-Fresnel's equation, and we can see that really in some case we can observe that our for example, red peaks are more intense than our blue peaks. And we can observe this part, but in experiments we can't see it, because the intensity of these peaks in experiments are really small. That's why we can observe. About conclusions about the big drops. In case of big drops, the diffraction between drops and the ray spacing tells the drop it can learn to affect when the colors also look inside. In such case, the version is relevant. the border between big and small drops almost 10 or 15 micrometers. And of course we have no one drop on the glass. We have a big quality of drops. That's why it's really important the drop position randomly. That's why we can say that we haven't some clear interpretation picture. That's why we can neglect the differentiation between different drops. And we have a random shape. That's why our picture are smooth. Okay, about our innovation. We set aside that Higgins finale integrals for dispersion calculated always used. And we can use every formulas for black disk, and we look at picture with in terms of order observed. But what we do? What about our innovation? We calculate the small drops can be approximated by black disk. Dispersion is important in big drops, and inverse order is an elimination calculated by range dispersion and intensity change. What about our conclusion? Phenomenon case by diffraction on the drop and the distance between drops. Dispersion inside the drop is important for big drops, and small drop we can approximate it by like this. Border between two types of drop is at 10 micrometers, and difference between drops is not important because of randomness of drops position. And relevant parameters are size of drops, size of dripping, and type of light source. That's all. Thank you for your attention.
Questions from the opponent now, please.
Could you open the allowance slide? Where is the light source?
This light source.
Thank you. And next slide. How have you done this graph?
Use program paint.net. For every pixels, we have intensity.
And what is the dimension of intensity?
What could you start, please?
Dimension of intensity.
What do you mean? We have a relative and our program have a small equivalent of intensity. It's part of this equivalent.
And next slide. And am I right that you said the distribution of drops is completely random?
I show you the photos.
And how have you done the photos of droplets?
Use the microscope, and we breathe on our glass which are in the
understand, thank you. And how can you make the wafer on the glass?
We breathe on it. We have a different method, but after experiments we understand that the most optimum is really breathe.
Thank you. There's no time for questions now. 3 minutes preparation.